We're now going to move into the kidney, and as we talk about the kidney, I want to begin by breaking it down to its functional unit. So the functional unit of the kidney is the nephron. So I have a very simplified diagram of what a nephron looks like here, and we're going to divide the nephron into two major components. The first component is the vascular component, and the vascular component includes the afferent arteriole, which will be taking blood to the nephron. It then is going to feed a collection of capillaries called the glomerulus, and then from the glomerulus we have a situation where we have another arteriole called the efferent arteriole taking blood away. The efferent arteriole then subsequently divides into peritubular capillaries. And these peritubular capillaries then are going to be surrounding all of the tubular components of the nephron, and then will eventually empty back into a vein and be taken away. If we take away the majority of the vascular component, then what we see here in yellow are the tubular components. The first portion of the tubular component is Bowman's capsule. So this is where the glomerulus will actually be surrounded by Bowman's capsule. And you'll also hear me refer to the space within Bowman's capsule called Bowman's space. And those are terms that I may just use interchangeably. The next portion we have is the proximal tubule. Now I have this drawn here as a very short straight segment. In reality it's a long and convoluted tubule, but just for simplicity's sake I'm drawing it and representing it as simply a small straight segment. So the proximal tubule then drains into leads to the loop of Henle. We have the descending limb of the loop of Henle and the ascending limb of the loop of Henle. This then will lead to the distal tubule, and the distal tubule then will empty into a collecting duct. And as you'll notice, what I have represented here is that a collecting duct may receive flow from many nephrons. Now there are some different processes that we need to understand with regards to how the nephron functions. And the first process is that process by which we are filtering material from the glomerular capillaries into the tubular components, or into Bowman's space specifically. So this process is called filtration. Some substances are then going to be taken from the tubular lumen and put back into the peritubular capillaries, and that's called reabsorption. And then there'll be a few substances that move in the opposite direction, that later on in the peritubular capillaries they're going to be put back into the tubular lumen, and that process is called secretion. So these are the three main processes that we will discuss as we talk about the kidney. Now the final product of all this will eventually be sent out of the body in the form of urine, and that would be called excretion. So let's look at this glomerular capillaries, because this is where filtration is going to occur. And one of the things we notice with the glomerular capillaries that's different than what we see in our typical systemic capillaries is these glomerular capillaries are what we say highly fenestrated, which means they have lots of pores or lots of holes through which fluid can potentially leave. So this is the capillary endothelium, which is highly fenestrated. Beneath this we have a histological structure that we call the basement membrane. And this is a structure made of a particular type of collagen and other substances, and this will also serve as a barrier to filtration. Finally, we have surrounding the capillary endothelial cells, we have cells called podocytes. And these podocytes have these interdigitating extensions that will form slits. And so we can demonstrate those on our picture over here. So these would be part of the podocytes creating slits. So this entire structure, including the endothelium, the basement membrane, and the podocytes, is referred to as our filtration membrane. So in order for fluid to be filtered, it has to pass through the fenestrations, through the basement membrane, and through these slit pores. Now another interesting characteristic of this is that the filtration membrane has a negative charge. And so what this is going to serve is that within our plasma we know that we have proteins. And these proteins are typically large as well as negatively charged. And so this negative charge of the filtration membrane is going to oppose the movement of these negatively charged proteins. So not only is the negative charge going to restrict movement, also the filtration membrane itself, these pores and these various barriers are small enough that they don't let proteins easily be filtered. Now, with regards to filtration, what causes the fluid to leave the glomerular capillary and enter into the tubule, or specifically Bowman's space? The forces that we see here are the same forces we saw with our systemic capillaries. So these are Starling forces. We just will name them slightly differently because of where they're located. So first we have our glomerular capillary hydrostatic pressure. So this is going to be the major force, which is going to be favoring filtration. Now on the bottom here, I'm going to create a formula, and so we're going to combine the forces favoring filtration. And first off, we have glomerular capillary hydrostatic pressure. We have our glomerular capillary oncotic pressure. So this will be created by the protein that's trapped within the glomerular capillaries. So that's going to be a force which is going to be opposing filtration. So we'll have those forces in a separate bracket here. We have Bowman's space hydrostatic pressure. So recall that this would correlate with the interstitial space hydrostatic pressure in our systemic capillaries, but when we talked about that, we said that the interstitial space in that setting was fairly ill-defined, and so we could easily understand how that pressure would be very low, and in fact we said under normal circumstances we considered it to be zero. But in this case, Bowman's space is a well-defined space within which fluid is building up. So there is a true Bowman's space hydrostatic pressure which will be opposing filtration. So we'll add that to our formula down below. And then finally, we have Bowman's space oncotic pressure. So this would be created by proteins that were in Bowman's space. But in a healthy nephron, we typically do not have proteins, so that force is typically zero. But if there were proteins that got into Bowman's space, that would favor filtration. So by taking all of these forces combined and taking the net difference between the forces favoring filtration and the forces opposing filtration, that gives us our net filtration pressure. This graph will demonstrate these forces just in a different setting. So on the y-axis we have the actual pressure. So if we insert the glomerular capillary hydrostatic pressure, it starts off high and it ends relatively high as well. So we'll see that's different than what we saw in systemic capillaries. The other force favoring filtration would be our oncotic pressure of Bowman's space, which we said is typically zero. We then have our forces opposing filtration, which would be our osmotic pressure of the glomerular capillary. And notice in this graph, as well as the previous slide, I drew an arrow that seemed to be increasing in size. In the glomerular capillaries, we're losing so much fluid with filtration that the concentration of protein left behind increases to the point that it actually changes the oncotic pressure within the glomerular capillaries. Hence, we'll show that line increasing as we go along the glomerular capillary. The other force opposing filtration will be Bowman's space hydrostatic pressure, and that is a pressure which is about 10 millimeters of mercury. So these are our various forces. So if we add these together, we can add the forces favoring filtration, and of course this line doesn't change because our oncotic pressure of Bowman's space was zero. And then we add the forces that are opposing filtrations together. What we'll see is along the entire length of the capillary, there is a net positive pressure which is going to be favoring filtration. So just for review's sake, let's take a look at the systemic capillary versus the glomerular capillary. With our systemic capillary, we had our hydrostatic pressure, but this pressure was one which decreased as we went along the length of the capillary. We have our oncotic pressure of the glomerular capillary, and in this case, we're not losing a lot of fluid, so that pressure stays relatively constant, and it's opposing filtration. And you notice that along the length of the capillary, these forces are going to flip, and so on the arterial side, we favor filtration, and on the venous side, we favor absorption. Now compare that to what we're seeing in the glomerular capillary. In the glomerular capillary, hydrostatic pressure is large, and although these aren't meant to be drawn to scale, this does emphasize the fact that the hydrostatic pressure of the glomerular capillary is significantly more than what we saw in our typical systemic capillary. And notice that it also stays high along the length of the capillary. We have our oncotic pressure glomerular capillary, which is opposing filtration, and once again we show that it's increasing as we move along the length of the capillary. And then we have our hydrostatic pressure Bowman space, which is also opposing filtration. But if we add those forces opposing filtration and subtract those from those favoring filtration, we'll still see that we have filtration along the entire length of the capillary. And this is why we have such a great degree of filtration. And in fact, we filter about 180 liters of fluid over a 24-hour period. Now, the kidney itself receives about 25% of our total cardiac output. So a quarter of our blood that is pumped to our body, about a quarter of that goes to the kidney. Now that blood that reaches the kidney, as it flows through the glomerulus, about 20% of that will actually be filtered. So with each pass, 20% is being filtered, but realize because we have such a high cardiac output, this is being seen over and over again, and we're able to add that together through the day, and so we're getting plenty of filtration into the renal tubule. And realize the importance of that is that in order to process the plasma, we have to get it filtered. We call this filtrate the ultrafiltrate, or the filtrate. I'll use those terms interchangeably, and realize that the volume of filtrate that forms is going to be directly related to the net filtration pressure. And the amount of filtrate that's formed is going to be related to the subsequent amount of urine that's formed. So if there's a way that we can adjust these pressures, the net filtration pressure, then we would be able to adjust the amount of fluid that's filtered, and in turn be able to adjust the amount of urine that's eventually formed.